Hey chemistry class, how's it going everybody? We just about wrapped up our last unit. Our last unit was on equilibrium and rate. Now, some of it we did throw a little bit out. Under these situations, I wanted to go ahead and speed things up and ease our load a little bit. So I've really tried to sort of bring the amount of work I've been giving you guys and the amount of time I'm asking you to spend on this class down quite a bit. So we definitely covered rate. We talked about that some reactions are faster than others, and we know that there's some different ways that we can utilize to speed things up, like increasing the surface area, right? Chopping things up really fine, or using a catalyst, or adding temperature, things of that nature to help us with the collision theory. But then we focused a lot on equilibrium and this reversible reaction and Le Chatelier's principle. As far as rate goes, there's actually a lot more that goes with it in terms of equations that we could write for it, chemical equations, and we can actually put numerical values to this, not just say speed it up. We can actually say how much faster is it going to be, and we can classify reactions in terms of orders. There's first order reactions and second order reactions and things of that nature. And so you might have heard of this stuff before, or maybe not. But if you're coming back for AP Chem, it's not a big deal. We will just cover it next year. If you're not coming back for AP Chem, then you're going to be fine as well. It's not something that you're going to encounter in your, in your everyday lives. So what we're moving into now is acids and bases. Acids and bases are super important to our world. We use acids and bases in everything from cleaning supplies to flavorings in our food. For example, acids are really sour, right? Like a lemon. And so it's in sodas and all kinds of different things. So we want to be able today to sort of start our unit by just trying to figure out what is an acid, like chemically, like the formula of an acid. What do they look like? How do you know if something is an acid or not? And so there's several different ways that we can use, several different definitions that we can use to identify something as being an acid or a base. Now there's some older definitions and there's some newer definitions. And a lot of times people think, the old stuff, we don't need to use it, it's no good, just use the newest stuff. And that's not really the case with acids and bases. It's not that the old definitions are garbage and wrong. It's that over the years they keep discovering more new and complex chemicals, and they need new definitions in order to classify them. But for the chemicals that we use in this class and in most general chemistry classes for that matter, a couple of the older definitions are the easiest to use, and they're the ones that we're able to use about 95% of the time. So let's go ahead and take a little look at acids and bases and see if we can figure out what's what. Alright, so here's our first definition that we're going to be taking a look at. It's the easiest of all of the definitions that we have to work with. It's called the Arrhenius definition. It's the oldest definition, and even though it's the oldest, it's still the one that we'll be able to use the majority of the time in this class. Now, before we do this, I want to warn you guys that there are a few chemicals that as we work through this stuff today, that they can be an acid or a base. So in one example, you might see the chemical as being described as an acid, and then in the next example, you might say, wait a minute, he just called that a base. But a second ago, he just said it was an acid. And so these types of things do occur. There's not a lot of chemicals that do this, but there are a few. And so we want to be aware of this going into it. We call chemicals that can do this, something that can act as either an acid or a base, amphoteric. So just kind of keep that in the back of your mind. Now, when we are dealing with the Arrhenius definition, like I say, this is the most common definition that we would use in our class. Most of the chemicals we have would fit this. What you're looking for are two things. You are looking for H plus, or you are looking for an OH minus. These are the two keys to the definition. If you see an H plus, you know that it is going to be an acid. So when we look at this example right here, I see HCl, and we have been doing chemistry long enough to know that that is an H plus combined with a Cl minus. This is going to be an acid. If you see an OH minus, so we look in this example here, you know that it is going to be a base. Now, when the H pluses are floating around, what will basically happen is this chemical will donate its H+, and this H+ just doesn't float around like an Na+ does. It'll actually attack water. And if you think about water, which is H2O, all of a sudden that H+ adds onto it and you get this molecule. This isn't super important for us. You will see some people refer to it though. It's called a hydronium. Now, if you see an H+ or you see an H3O+, just know that they're pretty much interchangeable. They mean the exact same thing. So this is the Arrhenius definition. Now, when we're talking about the Arrhenius definition, like I said, this works the majority of the time. Lots of chemicals we have use this form. For example, some of the most common we've used in the lab would be HNO3, H2SO4, HCl. We can see that in every one of these we have this H+ that's right in front of the molecule attached to some negative polyatomic ion. Those are all acids. A lot of the bases that we have seen would be things like NaOH, KOH, CaOH2. It's very obvious, very easy to see that OH in front. But we run into a problem though. Occasionally, there's another chemical that we have used in class that is a base that does not have the OH on there. And what that example is this guy, NH3. For those of you who've been paying attention, you know that this is an ammonia molecule. Ammonia is a base. It's very common. We see it in all kinds of different things. But there's no OH on there. So how do we identify this as a base? Well, chemists came up with a new example or a new definition that will take chemicals like this NH3 into account. And this definition is called the Bronsted-Lowry definition. So the Bronsted-Lowry definition still is in some ways like the Arrhenius definition. We're still looking for H pluses, right? So if I see an HCl or an HNO3, I'm still thinking acid here. What has changed is the definition of a base. Instead of a base being something that can donate, so basically it's dropping OHs off, right? Instead of something being able to donate OH minuses, it says that it just needs to be able to accept, okay? So it's going to receive an H+. All right, so if we look at this example here, we can see HCl. All right, that one's usually pretty easy to identify. That must be the acid. There's an H in front. But then we see water. Well, you know what? Water has H's in front as well. So which one of these is my acid if they both have H's in front? Well, look and see at the product side. What did it turn into? I can see that here the Cl has an H and now it does not. So what has it done? The H has traveled over to here and we see that this has turned into an H3O+. So by definition, we would say that the HCl is losing the H+. It's donating, right? And then this one is going to accept. So since this is donating, just like in the Arrhenius, that's going to be my acid. And since this one is accepting, it's going to be a base. Now, if we look at something like NH3, we can see the same type of reaction happening here. Let's go ahead and add this to water, right? We know that this is a base already, so it's going to accept hydrogens. So what's going to happen here? This H is going to come over, and what are we going to get? You are going to all of a sudden have the NH4+, which we should recognize as the ammonium ion. And then what's left over? If the water loses an H, what's left over? OH minus. Now do you see it? Do you see all of a sudden that OH that it's supposed to be donating for Arrhenius? It's made visible. We can see that it's accepting a hydrogen. So now here, this would be the acid because it's donating, and this one would be the base. All right, now all of a sudden somebody might have just said, wait. You said that water was a base down here. Now you're telling me that it's an acid? It's amphoteric. It's one of those examples of an amphoteric substance. Now, remember that water, it could be acid or base, and this is sort of a shift for some people. We always think of water as neutral, okay? Now, that's not always the case, and we're going to learn more about pH and what it means to be neutral here in the coming days. Now, there's one other thing that the Bronsted-Lowry definition does for us. It takes into account the idea that we learned in this last unit that some reactions are reversible. So if we draw this other reversible arrow in here, that would mean that if you're going in reverse, we should be able to classify these as acids and bases as well. And that's usually pretty easy to do because that's got the H in front. That's the only one that can donate an H. So that would be an acid. And then the Cl would be my base, right? So if we put these down to here, all right, so there's my base because that's the only thing that can accept. That's the only thing that could donate. So that's usually pretty easy. Now, there is something that we need to do, though. You don't want to say, hey, the acids are the HCl and the H3O+, right? We want to distinguish between what's on the reactant side and the product side. So we have a word that we use. It's called conjugate. So this is a conjugate base, and this is a conjugate acid. Okay? And you'll notice that whatever it started out, so the chlorine started out as part of the acid, on the other side it'll always be the opposite, right? That's what it means to be a conjugate. So this is the Bronsted-Lowry. It's where we're just focusing on the H's. But what if we don't have H's? Now all of a sudden it gets a little bit trickier. These first two definitions are the ones that we will use 95% of the time in this class. Occasionally, especially at the upper levels of chemistry, you might run into something that doesn't have any H's in it. And in order to identify that, you would use the Lewis definition. So the Lewis definition is looking at electrons instead of H's. Okay, so some people might say, well, that has H's, but they're not in front. Those are not H pluses. Okay, this is a covalent compound. There's no donating of the H pluses. And so we're not going to go by the Lewis or the Bronsted-Lowry for that. So when you're doing this, one of the big key ideas that helps you spot a Lewis definition, it usually forms only one thing on the product side instead of having two, right? So if we look at that, there's two products. We look at that one, there's two products. Okay, so whenever you're seeing something that's coming together and you see two products, it's usually one of the first two definitions. But the keys here are off to the side. Look for positive ions. Look for things that have less than the full octet if you want it to be an acid. If you want it to be a base, right, then you're looking for negative ions, or you're looking for less than the perfect amount of electrons. To be honest, most of the time you can tell just from this one and this one. You don't need to go drawing out a Lewis dot structure to figure this out. Not with the questions that I would be giving you. But if you were, in this particular example, there is no positive, there is no negative. But if we were to draw this, does this guy have his full octet? No, this one does not. If you draw out the NH3, this one has extra electrons. This one doesn't have enough, so it's going to take both of these extra electrons and form a bond here. Okay, so this is what we're talking about with the Lewis definition. So this one here would be, so a base is anything that donates an electron pair. So this guy right here is going to be a base, and this guy right here is going to be an acid, and then you wouldn't have any conjugates that you would worry about on the other side. Like I say, these are very, very rare. We don't see a lot of these. Now, the last thing I wanted to point out was remind you guys of the acid-base reactions. Remember that acids and bases are really dangerous to us when they're in strong, high concentrations. We say that they're corrosive. When something is corrosive, it's going to destroy, it's going to damage, it's going to mess up stuff. If you look down at these pictures I spotted here, this guy spilled some acid on his hand, and you can see within seconds, this really high concentration stuff burns right through you. This girl off to the side here, this was actually an older story a few years back in the news. This lady, she was a model actually. She walked out of a department store and somebody was out front and they just said, "Hey, pretty lady," and they threw a bottle of acid in her face. And you can see that it burned her face really, really bad. So this stuff really destroys skin. You do not want to get acids and bases on your skin. If you do get an acid spill or a base spill, what is neat is if we remember back to our types of chemical reactions, when you have an acid and you have a base, if you mix them together, what do we get? Salt water, which is totally harmless. So if you spill an acid all over the floor, then you open up the bottle of base and you start dumping it in there in order to neutralize these things and really remove some of that danger from it. So let's just take a quick look at a couple of examples. I have some examples here. See if we can identify what definition we would use, and then we're going to try and figure out what the acid is and what the base is. So if we look at number 1, we want to try and figure out what definition we would use. So I always start in the order that I gave in the lesson. I would go with the Arrhenius first. Arrhenius looks at H's and OH's. Do I have any H pluses or OH minuses in this reaction? No, I don't. So I'm not going to use the Arrhenius. So I go to the next one, Bronsted-Lowry. Do I see H pluses that could be moving around here? I don't see any H pluses, so I can't use that. So what does that leave me with for my last definition? The Lewis. Let's switch colors. So I would use the Lewis definition for this. Now, if we're using the Lewis definition, it says that anything that has extra electrons to donate is a base. And I see extra electrons right there. So this would be the base, which means by default, that has to be the acid. If you see a base, you should always see an acid. Let's take a look at the second one now. If I look at the second example here, what definition do you think we should use? Start thinking through your head and see if you can identify what definition would be best. All right, so when I look, I see some H's in front, but do you see any OH's? No. So the Arrhenius probably doesn't sound great in this example, but since I do see the H's, I'm going to go with the Bronsted-Lowry definition. So if I'm using the Bronsted-Lowry definition, we know that the thing that donates H's is the acid, and the one accepting H's is the base. So if I look right here, I see the NO3 has an H, and on the other side it doesn't. So it must have donated its H to here. For me, when I'm doing Bronsted-Lowry, I think it helps a lot to actually draw the arrow. So if it's donating, this is the acid, and that makes this the base. So since it's Bronsted-Lowry, we also want to think about the reverse. So we should label the acids and bases on the other side as well. And that's usually pretty easy. If the NO3 was part of the acid, it's going to be a base on the other side. And so this would be the acid. And that makes sense because here we have H's and here we don't. So if you don't have H's, you can't be an acid, according to Bronsted-Lowry. So since these are on the product sides, I'm going to call them conjugate acids and conjugate bases. All right, let's take a look at number 3. Scrolling through our different definitions, what definition would we use for this one? I would probably pick the Arrhenius definition for this one. If we're using the Arrhenius definition, what's the acid and what's the base? So this one has H's in front, this one has OH's at the end. So this would be the acid, this would be the base. And I wouldn't have to worry about labeling the right-hand side because it's not using the Bronsted-Lowry definition. One final one here. Looking at this equation, which definition would you use? Well, I see some H's in front, but I don't see any OH's hanging off of the end. Now, maybe an OH over here, that could be possible, but that's not where we start looking initially. We only see it on the reactant side. I don't see any OH's. So I'm going to go ahead and use the Bronsted-Lowry. I think that's pretty safe. So this is going to donate an H over to here. So I like to show the arrows, remember, which makes this an acid and this a base. So if this CO3 was a base on this side, it must be an acid on this side, and that makes this the base. And that makes sense. This could donate H's. Since they're on the product side, we would call this a conjugate.